Alrighty. These will be fun.
I know it used to be easier than stuff. Like for all the big stuff. Things are so simple.
Is this your favorite subject, oscillators? No. So we'll talk a little bit about types, how to stabilize them, some things like microphonics, digital versions. So they're claimed to be a building block, basic building block. In essence, you need pretty much need an oscillator, even if it's digital, and you're digitally generating your VFO and beat frequency oscillators, all those kind of things in the digital domain. You still at least need a clock signal for the signal processor. So even in the digital one, you're going to have an oscillator. Normally, they're used to generate the signals that we transmit.
With digital, everything's time critical.
Yeah. They're definitely part of the old super heterodyne receivers, and they may have multiple oscillators in them. It's just an amplifier that has a tuned circuit providing positive feedback. Enough feedback to overcome the losses in the circuit and to keep it oscillating. They say the best way to build an oscillator is just to build an amplifier, and it'll probably oscillate if you didn't do it right. So it could be an LC circuit that is the frequency determining component, or it could be a piezo crystal. And we'll talk about that type as part of the group. We're basically going to talk about three: Colpitts, Hartley, and Pierce. And here they are.
Like a law firm.
Yep. Colpitts, Hartley, and Pierce. And they're all dead. Colpitts, and the way for me to remember the Colpitts, it starts with a C. So the feedback, well, there's Ernie, comes from a capacitive divider. That's why I remember it with the C.
Should look like Jack, I think they're. Oh, no. They sit there. Yeah. Like it'd be hard to see the screen. I don't mind sitting next to me.
And they're normally used as a variable frequency oscillator because we can vary a component in the LC circuit, either the inductor or the capacitor. The Hartley is getting its feedback from a tapped coil. And that's the basic difference. The circuits are very similar, except how you provide the feedback. It's through the capacitive divider and the Colpitts, and the inductive or tapped coil in the Hartley. The Pierce is the one that uses the crystal as the feedback element and as its tuned circuit.
So I remember Hartley because the inductor is in Henry's.
Okay.
H.
Henry's.
And then Pierce is a piezo.
Yeah.
Right. Pierce is a piezo.
PQ come in the same series in alphabet, right? OPQ, yeah.
Yeah.
So PQ, Hartley, Henry's, Colpitts capacitors.
Okay, what are three oscillator circuits used in amateur radio equipment?
The law firm of Delta.
Delta. We may be entitled to conversation.
It's Pierce, Fenner, and Bean. I wonder if that's a real company. Which of the following oscillator circuits are commonly used in VFOs?
Baker.
Very good. Okay, here's a Hartley, and you see the tapped inductor. It's a little strange the way they normally draw them, but you're seeing essentially half of the signal being fed back into the amplifier or the transistor. And your tuning is this is the variable capacitor. Could be a varactor, or it could be a manual rotary capacitor. So how is positive feedback supplied in a Hartley oscillator?
Henry's.
Alpha.
Very good. The Colpitts looks about the same, except we get the feedback from the capacitive divider, and we take that tuning capacitor and split it in half. We're still more than likely tuning it with the capacitor. It could be two varactors or a dual variable capacitor. So how is positive feedback supplied in a Colpitts oscillator?
Charlie.
In the Pierce, ooh, it's a little bit high there. Huh. Feedback is done through the quartz crystal. And in order to make sure that it's on frequency, you have to supply an external parallel capacitor specified by the crystal manufacturer. And it may, it can vary depending on the cut of the crystal and the frequency.
But you can roll your own.
You can roll your own, and sometimes they'll oscillate without the capacitor. How is positive feedback supplied in a Pierce oscillator?
Delta.
Which of the following must be done to ensure that a crystal oscillator provides the frequency specified by the manufacturer?
Baker.
You can actually shift the frequency a little bit by varying that capacity. In fact, you can make it somewhat a tunable oscillator by using a varactor in parallel with it.
So that's what the old novice radios did, that were slightly tunable.
Yeah. You can't move it much, but you can shift the frequency.
We're still using a crystal.
Yep. Or you can heat it up, but you have a lot of control. Thermal drift. Okay. LC oscillators can drift due to the capacitor heating, and as it heats, basically the dielectric expands and the plates get farther apart, so the capacitance decreases. And that's going to change your tuned circuit. One of the things that you do is use what they call NPO capacitors, which have a negative, like, temperature coefficient. I don't remember what NPO stands for, but they're much more stable over temperature.
CPO, you know anything about NPO? No, I used to use it, but I don't remember.
What it stands for? I'd put that on my action item list.
Yeah,
I think I knew once.
I was back and forth between two or three different references on this, and in some references, it has a zero there instead of an O. And I mean, the difference when you.
Well,
look
it could
at
be
the
NP
text,
zero,
the
yeah.
O is always wider, and the zero is a narrower figure. And so, but I couldn't come up with an answer on it. But I just know that from the distractors on the test, there will only be one that says NPO.
Yeah. But basically, the capacitance change is very stable, changes very little over its operating temperature range.
I was talking to, I think it was Byron I was talking to. I've got, my radio is very, very susceptible to AM broadcast. And I am 2,347 feet from a 50,000 watt AM transmitter.
Oh, wow.
So, but the good part is that it's restricted to daytime use only. The
Ah,
FCC told them they have to shut down at night, not
okay.
interfere with emergency services. So, at nighttime, I can turn on the radio. So as the sun hits the horizon, I've got a good signal, but otherwise I'm listening from 1.8 all the way up to 30. All I can hear is that AM broadcast. So, and I was talking to Ernie about, or Byron last week at the chili dog social. And he said I need to get a filter or either get or build a filter. So I found a filter online, $20 for the kit. And it's only a 20 watt filter, so which works fine for my radio, but not for everybody. But 20 watt filter and a kit, a circuit board and 3 inductors and 3 capacitors and a couple of connectors. And he mentions in there that he uses only NPO capacitors.
Okay. So which of the following components can be used to reduce thermal drift in crystal oscillators?
alpha,
Must be NPO capacitors.
That actually looks like that's a 0 there.
Exactly.
Stabilizing of it.
Yeah, right. But that's not on the list.
Oh, okay.
Microphonics is another potential problem. And you can have frequency changes due to mechanical vibration. It can affect the crystal. It can affect inductors and capacitors. So one of the things that you can do is to isolate the oscillator circuit from its surroundings, so you get less vibration transferred into it.
Don't put it in the vehicle.
Yeah, but those are low frequency as you do the humps and bumps. What is a microphonic?
Charlie,
How can an oscillator's microphonic responses be reduced?
delta,
You build it on a rubber circuit board, right?
Little elastic bands.
Direct digital synthesizer. Now we're going to have a digital oscillator. They tend to be much more stable because they're typically generated from a crystal reference oscillator. You've got kind of 2 kinds, a direct digital or a phase lock loop. In the direct digital synthesizer, they basically simulate the sine wave by what they call a phase accumulator, and it just generates steps of the waveform cycle. So depending on how many samples or steps there are, determines how much phase difference there is for each one of the samples. And as it steps through those, it takes that output and just does a lookup, either in a read-only memory or in the DSP itself, where it's already pre-programmed with what the sine wave output would be for that particular phase of the sine wave. And then it takes that output and then runs it through an analog to digital converter to get rid of the steps, basically, and convert it into a smooth sine wave. And it also uses one of those anti-aliasing filters to get rid of those high frequency components. So it's essentially a counter a lookup table and a D to A converter.
And you said it converts it back to a waveform.
Right.
Why would you want to do that?
Well, you generate that's what you want to generate.
Oh, okay.
You're trying to generate a sine wave at some frequency.
Right.
So,
But
the-
couldn't you just take the digital and work with the digital?
well, this is digital.
I know, but you said convert it to a sine wave.
Well, I can't send a 16-bit digit to an antenna.
I guess that-
I need to send the sine wave to the antenna.
Right.
So in order to generate the sine wave, okay, I do it by synthesizing it. Okay. Because I've got a table that has all the values for the sine wave in one cycle for essentially every degree or whatever, however many
Waves.
steps that you want to divide it up into. And you're basically, if I was generating a 1 megahertz sine wave, I might be clocking that phase accumulator at, I don't know, 10, 20, 50 times that in order to get a nice, smooth sine wave. But with this process, it doesn't have to be a sine wave. I can put any waveform in that table, and for every input, okay, and I can produce a square wave, a sine, sawtooth, a triangle, trapezoid, anything I want.
What type license do you need to do that? Is that regulated by the FTC?
Not until you connect it to the antenna.
The FTC's involved? Wow. You own your own.
So what type of frequency synthesizer circuit uses a phase accumulator, lookup table, and digital analog converter, and a low pass anti-alias filter?
Alpha.
Direct digital. What information is contained in the lookup table of a DDS?
Baker.
Right. Right. And it says desired waveform because the waveform can be anything you want that you've programmed in that lookup table. So if you want to build like a piece of test equipment that's a multi waveform output signal generator, you just have multiple lookup tables that you'd switch to depending on what output you wanted.
I'm trying to figure out where's my baseband signal. You know, I got a baseband signal that I need to modulate, right? So how does that work in here? That's, in other words, I got a carrier and then I got baseband with the previous slide. How I'm trying to make sure I understand how all that comes out with the diagram you just presented.
Well, this is just a way to generate an oscillator signal.
Oh, just the oscillator. Okay.
Right.
No modulation.
Instead of being an analog oscillator, this is a way to digitally generate the waveform.
And you need a clock, initial clock to come in to do it, right?
Right.
Yeah. Okay.
Even if it's digital, you require at least one clock signal for everything to work.
Okay.
So the other method is phase lock loop. And it's really just a servo loop, and you have a phase detector, a low pass filter, a voltage controlled oscillator, and a stable reference, which is usually a crystal oscillator. So you can not only synthesize a waveform, in this case, it's basically going to be a sine wave, but you can also use it to demodulate an FM signal instead of using the discriminator or ratio detector.
Which is the most common in the digital, or what's the most common used now in digital radio?
for,
Is there any that really wins out, like the phase lock loop?
I think they're probably doing direct digital more than the phase lock loop, because phase lock loops are not new,
Right, that used to be from,
right?
That's
Analog.
what they,
analog where you.
Right.
that's when, before, they were almost all
Phase
phase
lock.
lock loop because
Right.
the circuits weren't fast enough to take it. Your clock has to be a lot faster than the output signal, 3 times desirable.
But you can use the phase lock loop as a synthesizer. And it's kind of a hybrid between analog and digital. So you're taking your reference oscillator down here, and you can run it through a divider. And you wind up with, you can set up a ratio to get different frequencies. So you take that divided reference frequency into the phase comparator, and you're comparing it to the output of this other divider, which you can vary. And that's feeding the output signal back in. So you're going to compare your output signal back to this reference. And if they're out of phase, you're going to get an error signal, and you filter it to keep it basically a DC error. And you change the frequency of the VCO. So that will quickly close the loop, and it'll settle on a frequency that is determined by this divide ratio and whatever you divided the reference oscillator by. So between the two of those, you can, if you do it right, you can get just about any kind of frequency down to maybe a hertz. And they work quite well. And like I said, it is kind of a hybrid. You've got an analog loop and digital dividers and a digital, in fact, that oscillator could, I guess, be a DDS, but it'd be simpler just to use a crystal. So what is a phase lock loop circuit? Are you sure about that?
Definitely servo.
Charlie.
Charlie? It's a servo loop, but it doesn't have a reactance modulator in it.
Charlie.
You were close.
The one that's got a phase detector in it.
And it requires a phase detector.
I mean,
So which of these functions can be performed by a phase lock loop?
Delta. GMR.
Delta.
Yep, you said that.
Can actually be used in radios for frequency control. The old tracking system on Apollo had phase lock receivers, and they would lock onto the frequency of the signal because it would vary because of Doppler and all that good stuff, and you could track it. Oh. Okay. Spectral purity is an issue with both of them, where in phase lock loops, the bigger problem is called phase noise, because if you got that loop closed, any error in there causes like phase jitter. With the direct digital synthesizer, you're more prone to getting spurious output from the steps. And this one is showing a sample output from a direct digital synthesizer and what they call the spurious free dynamic range, where it's the difference between the the output signal and the highest spur. And I think there's a spec of,
40 dB.
excuse me,
40 dB.
is it 40?
Yeah.
In this picture, I don't remember what the requirement is. Whether it's
It
40 or
varies by
50.
How far away from the reference signal.
Okay.
I don't remember the numbers.
What are the major spectral impurity components of a direct digital synthesizer? Yep. Spurs at discrete frequencies.
Yep.
And high accuracy oscillators. I guess you use frequency multipliers both in FM transmitters, because you normally do the modulation at a lower frequency and then multiply it up. And I guess at some of the UHF and above, you also have to use multipliers. So one of the techniques to get it more stable is to use a GPS signal reference and what they would call a GPS disciplined oscillator, where you're feeding the GPS 1 hertz clock signal in and syncing your oscillator to the leading edge of that 1 pulse per second. And it's very, very accurate, down to tenths of a hertz.
Can I use the temperature control IQ dielectric resonator on my porta pipe car?
On which car?
The porta pipe, whoa,
Maybe.
maybe.
I've never seen a temperature controlled high Q dielectric resonator. I have some ceramic resonators, but they're not temperature controlled.
I've seen two of these big resonators on the porta pipe.
Oh, okay. And then you can have a rubidium stabilized reference.
Only if we have a lot of money.
Yeah,
That's what I was gonna say. That-
probably takes a lot of money for the temperature controlled dielectric. I don't know. But GPS is easy to come by. GPS receiver today is $20 with the antenna.
It has the rubidium standard on it for you. So you don't have to pay for it.
Well, there's a rubidium standard somewhere. I don't know that it's on the receiver. Which of the following is a technique for providing highly accurate and stable oscillators needed for microwave and reception? We got our first all the above.
Yay.
There aren't many on the extra. Surprising. They have a lot of them on the technician.
Stop recording.